Okay, we're going to go ahead and finish up this example here in number 1, part D. We're looking for the error of the function now and express the error as a percentage of the integral's true value. So all we're going to do is we're going to examine this initial value we've gotten for the error, and that's one way or the other the true answer could be. So to find the error, all we have to do is use the formula here and take the value, which was e sub t, which is 0.16149, divide that by the true value that we found. In this case, we were able to calculate it exactly. If not, you might have to use a calculator for that. And then we multiplied times 100, and we received the number that was 8.07. And I have a discrepancy with how we use this 100. So understand, we're looking for percent error. When we multiply by 100, we're actually getting a whole number, but let's just put this in our calculator and see what I'm talking about. And I don't quite agree with how sometimes people write these things, so therefore I want to go ahead and examine it. Now you notice if we do that, we get 0.0807, which is 8.07% error. So we really don't need to multiply by 100, and really shouldn't. We should just leave it as that, and then that's equal to 8.07%, because remember the percent symbol means divide by 100. So that's good enough. So let's move to example number 2. Okay. So example number 2 is a little bit different. Not much more to do, but we're given a problem that the speedometer reading on a car was observed at 1-minute intervals and recorded in the chart. And we want to use the trapezoidal rule with n equals 10 to estimate the distance traveled by the car. So what does the distance traveled by the car really mean? Well, it's the definite interval from 0 to 10 of the velocity function, okay, integrated, dt. So that's going to be approximately equal to a bunch of trapezoids. Now, let's examine our t values, and notice they are very nice and even partitioned, so we could use the direct trapezoidal rule that we knew it to be. So here's how we would set it up. So this is approximately equal to, now we notice it's going to be 1/2, right? 1/2, and it's going to be b minus a, which is now 10 minus 0 over n. In this case, it's 10. So that's going to be our outside. And now in here, we have a bunch of trapezoids. Now there's so many here to mention, but let's just give a representation. It would be 1 times the first one, okay, f of 0. In this case, it's v of 0, plus 2 of v of 1. And we would keep going until we got to 2 v of 9. Then we would finally add 1 of the v at 10. Okay, so let's go ahead and put all those numbers together. Not much, it's just a bunch of organization now. Keep track of our numbers, don't make a mistake. This is pretty easy on the outside. We just see 10 over 10 is 1, and half of 10 is 5. Okay, so let's just write the numbers down. The first v of 0 is 40, plus 2 times 42, plus 2 times 45. And we can continue, and we will, plus 2 times 49. So don't make a mistake. 2 times 52 plus 2 times 54. And we're almost getting to the end. Hopefully we'll have more room. 2 times 56. Let's write smaller. 2 times 57. We've ran out of room, so let's bring it down here and write 2 times 57 again. And then finally 2 times 55. And this is monotonous, so we get to end with 1 times 56. So let's group it. Now I'm assuming that we could all add those up manually. We notice that that wouldn't be too hard to do, and if we did that, we would work our work down, and on the most problems you'll be expected to do this pencil work. Won't be as much, but you'll expect it to get an answer of about 515. Okay, so that's pretty much it. That's how you do that. So let's go do a couple problems from our homework to see how those would look. Okay, I'm going to go ahead and look at problem number 1, and all it asks us to do is estimate the first one. So again, 1 is the integral from 1 to 2 of x dx. We know we could do that without estimations. We could say this is just x squared over 2 evaluated 1 to 2, and that would be then 4 over 2 minus 1 over 2, and that would be 3 over 2. Okay, that was fun. We got that one done, and that was quick. So now how would we do the trapezoids? Well, to do the trapezoids, we could look at the graph. That would be one way to look at it, and a lot of times it's not a bad way to do that. So let's go ahead and look at the graph real quick and see what this problem is asking for. I think it asks us to use 4 partitions, okay? So it's a pretty simple graph to do. It's y equals x, so let's just go put y equals x in. And if I'm going to go from 1 to 2, I'm going to go from here to here roughly. Okay, so that's 1, and that's 2. And I know that if I'm going to go 4 partitions, this in the middle is going to be 1.5, and this one here would be 1.75, and this one here would be 1.25. Okay, so the area, in this case, notice the trapezoids are going to be exact now. So you should not get any error because the trapezoids, because this is linear, that's the first trapezoid, second trapezoid, third and fourth. So not much to do here other than write the equation. So we should understand that the trapezoid is an approximation, and even though in this case I know it will be an exact amount, but it's 1/2 times b minus a, which is 1, over n, which is 4. Okay, so it takes care of those. And now I have 1 of 1, f of 1, which is 1, 1 of 1, and then plus 2 of 1.25, plus 2 of 1.5, plus 2 of 1.75, and finally plus 1 of 2. Now, those are all even partitions, so I can apply this rule here pretty simply. If we do that, we then see our approximation is the same as our exact answer. It's 3/2. So the question is now find ET. So the maximum error for our function for this one would be b minus a, which in this case is 1 cubed, divided by 2n. Okay, so I'm sorry, it would be 12n squared, 12n squared, 12, and then n squared is 4 squared. And then finally, it would be the max value of the second derivative. Well, the second derivative of my function is 0. So you notice my error in this case is going to be 0. It knows if the second derivative is 0, it knows it's a line. So therefore, there's no error there. So therefore, my percent error is going to be 0. Okay? Okay, I want to take a look at problems 7, 8, 9, and 10. So it talks about using the given information about f of x and to determine its derivative, looking at its derivative to determine whether the trapezoidal rule would be an exact, underestimate, or overestimate the integral for there or not enough to tell. Okay, so that's the idea. So to do this in each time, what we really want to do with our function is kind of get a representative graph of what it might look like. So if we do that, it'll give us a picture of what we would expect the trapezoid to look like. Number 7 is saying the second derivative is greater than 0, which means it's concave up. So let's kind of look at number 7. It's concave up, and the first derivative is greater than 0. So it's increasing. That means I'm looking at this side. So I'm looking at a concave increasing function. So let's draw a trapezoid on this one. All we need to do is draw one nice big trapezoid. And we notice that if we draw a trapezoid, it goes over. It's going to be an overestimate. So this is an overestimate. Okay, so that would be how 7a would look. Number 8 says a concave up because it's positive, and then the derivative is negative, so it's going to be the decreasing part. It's going to be something that looks like this. So if I look at the concave, or not the concave, but I look at the trapezoid, I notice in this particular case, again, it's going to be an overestimate. Okay, overestimate. So then this was number 8. Let's do number 9 here. Number 9 says its second derivative is negative. So that means concave down, first derivative positive. So we look at a concave down, and we're looking at the first derivative is positive for number 9. So that's the part of the curve we're looking at. So let's draw that curve. That's good enough. Now we go ahead and put our partition. We show it, and we could clearly see that we have an underestimate for that one. So we'll put now underestimate. And finally, for number 10, it's going with first derivative. And that one, let's do second derivative first. That's what it lists in a problem. Second derivative, less than 0. First derivative, less than 0. So we're concave down, decreasing. Concave down and decreasing. So again, draw a little sketch to make your final determination. And so there we have it. Again, we have an underestimate. Okay? So number 11, let's kind of look, let's put number 11 right here. First or second derivative is equal to 4. Now, the second derivative is equal to 4. It's positive. And the first derivative is greater than 0. It's increasing. So it's a positive second derivative. That means it's concave up, and it's increasing. So we're going to get something that looks like this. Okay, now it's very determinable. Now remember, just because it didn't say less than or equal to or whatever, it's clearly that. Now, at 4 means it's pretty good. Okay, so let's go here, and let's go here, and notice we get a overestimate. So overestimate. I encourage you always to check your answers before you move on. Finally, let's look at problem 13. We have about a minute and a half, so let's set up and we'll do that one. Okay, in the last roughly 2 minutes here, we'll cover these problems 12 and 13. Again, 12 is asking you to use the trapezoidal rule with 4 equal subdivisions on the interval from 0 to 1 to approximate the output. So really it wants to find the definite integral of an integral function. Sometimes when you see the integral going from 0 to x, that's an integral function. We're defining a new function, big F of x, to be the accumulated area from 0 to some n value x. And x can be both positive and negative. So don't assume it always has to be a positive number. So what would you do there? You would just go ahead and work the trapezoidal rule with the fact that you're using 4 equal partitions. So you would go and divide it accordingly. Okay? And you're going to, in this particular case, from 0 to 1, so you'd go 1/4, 1/2, etc. Now, you're going to use your calculator to then estimate those values for the sign. And you see now, as I would use my mouth to highlight, you see the values that I plugged in, and then I get the answer. Okay, finally, the sine function is positive as it goes from 0 to theta, and therefore would increase. And when t squared is less than theta, it's okay. So t squared is greater than 2 theta, but t is that. And so on what intervals is it increasing? So we just want to make sure we understand when it's going to 1, what's happening. So there's my sine chart. I'm checking it out, and then it asks for the average rate of change. Okay. Now, problem number 13. Let me go ahead and show it a little bit bigger here so you can get the whole thing to look at. and look at the work that's done there. And if you don't understand anything, please see me in class. Okay, thanks a lot. Have a good time.